Let us look at thin-walled pressure vessels. So the name itself indicates that the wall is thin. So what is the definition of thin? If the thickness is 1/10 of its radius, you can claim that to be thin. That means the radius over the thickness, right? If R over T, let me, is greater than or equal to 10, so radius is 10 times thickness. We can say that it is thin. What happens in members of this nature? Look at this picture here. It's a tank, cylindrical tank. Let's assume we're filling this with water, or let's say we're filling this with gas, and we keep increasing the pressure. What are the stresses induced in the material of this tank? So if you take a tank and if you take its, let's say, we take its, we take a tank and let's say we take a small part of this tank. That means let's cut it like a piece of cake. Let's cut it here. So what happens to the material? So this is the thickness. So that is thickness T. What happens to this thickness is what we will be trying to see. We'll be trying to calculate due to the presence of some gas inside the tank, what will happen to the material. Two things will happen for sure. Assuming that this is a cylindrical tank, when we fill this with gas and we increase the pressure, let's keep increasing the pressure, what happens? One thing is this circular that would expand. That means the radius will increase, right? If we think this is radius, the radius will increase. That's one thing that is possible. The other thing is the length L, assuming that we close this, we close this, and we close this side. No place for the gas to escape. The length will increase as we increase the pressure, right? So increasing pressure can cause two things: increase the length of the tank and increase the radius of the tank. Two things can happen. So how can we estimate how much increase in R would happen and how much increase in length will take place? How can we estimate that? By making a cut and by expressing stress in terms of pressure, we can try to get some information from that. So by the concept of pressure, we have to be careful with the concept of pressure. Pressure is same at all places. So pressure here is same as pressure there, is same as pressure here, is same as pressure there, is same as pressure here, is same as pressure here. So pressure at every point in the tank is the same. So pressure is same at every section at every point inside the tank. By the way, the tank is of thickness T, right? The tank has thickness T. And being thin, it is 1/10 or less. If thickness is 1/10 or less, we can claim it is 1/10 or less of radius, 1/10 of radius or less, we can claim this is thin wall. So how can we bring a relationship between radius and pressure, length and pressure? How can we bring a relationship? That's what we'll see now. To do this, we have to make a cut, right? Let's make a cut as shown here, as shown here. That means we can take a plane let's cut it like that, parallel to length. That means we're making it into half. That means we have, so if you observe it would be like this, isn't it? After we make a cut, it's actually semicircular, this part. So this is the thickness. This is the thickness. So that means we made a cut like this, right? We made this into half. Now, to this section, we will again cut it like that. That means we will only take this part of material, which would appear like this here, which should appear like this. Let me draw. That means that part will have, because this is a tiny minuscule part, we can say this is dy, and the inner radius, this being r and that being r, the total length will be 2r, and thickness being negligible, so the thickness is this. That is the thickness. That means this member thickness is T. Remember, the pressure is being applied. So if we take this cross section, only that part, we draw in black color. So if we only take this part, okay, what is the force acting on that cross section due to the pressure P? It is nothing but pressure times area. The units of pressure are Newton per meter square. So we have to multiply that with meter square to get the force, right? So it is basically pressure times area. So what is the area of this cross section? That cross section area would be length times width. So the total length will be 2r plus 2t, isn't it? Times dy. Because there is a t here, there is another thickness here. So this is 2t and 2r. So this is the total force acting on that cross section. But where is the material? The material is only present here. Material of material with whichever material we're making the tank. We can make it with steel, we can make it iron, we can make it copper, we can make it zinc. It's up to us. We can make it with an alloy. So the material is basically the highlighted thick black. So what is this area? That means how much force, how much resistance force is this highlighted, two highlighted solid blacks are giving. So basically these two highlighted solid regions are opposing this much amount of force acting on the member, right? Right. But by the way, if you observe carefully, I have to remove this 2t here because one thing is that the pressure inside the tank is only here wherever the gas is in contact. So the gas is not in contact here, neither the gas is in contact here. So sorry, I have to remove the 2t. So this highlighted solid black with this red color border, that is the material that is opposing P times 2R times dy. So let me write times dy. So this is being opposed with the stress developed. Let's say the stress developed is sigma, the solid black, times what is the area? Area is dy times t, and there are two of them, right? Right? This one and this one. So both of them combined, dy times t. Dy is this horizontal, t is the thickness, and you have two of them. So sigma times dy times t times 2. So the dy here and dy here gets cancelled. So what we get is sigma is p times 2r over t times 2. So 2's get cancelled. So sigma is basically p times, so pressure inside the tank times radius of the tank over the thickness. This is the stress. So how does this stress act? This stress acts out, right? So this opposes this pressure acting in the tank, right? So this pressure or this stress developed is not only on this highlighted, we just took a thin small strip, but it is not just on that solid black color region, but it is all along this section that you made a cut. And we can make it so all semicircular cuts. So we take a metal. So when we actually make it into half, no matter how we make it half, either vertically or horizontally, the sigma developed will be the same, will be this one here. So that sigma is called hoop stress or circumferential stress. So that is called hoop. Hoop direction means, if you observe, it is, so if you observe the hoop direction is sigma 1 along the circumference. You see, if you observe this picture carefully, uh, if you observe this picture carefully, the sigma 1 is along the circumference. We call that hoop. So what we calculated now is the hoop stress. So sigma 1 developed due to pressure inside the tank is given here, P times R over T. Similarly, we should get sigma 2. It is longitudinal. That means sigma 1 will cause increase in the radius, sigma 2 will cause increase in the length, pretty much. So if you look at the textbook, there is a derivation for that because I explained one. You can look up the concept, how to get the longitudinal stress. It is P times R over 2T. It is something similar. This is hoop stress, right? This is hoop stress. What we will get next is longitudinal. Longitudinal stress. and that is sigma, let's call it sigma 1. The sigma 2 longitudinal stress is P times R over 2T. Basically, you need to know these two formulae. Okay? All right. Proceeding further. For example, in Midland Odessa region, in our region, we look at different scenarios where we see a spherical tank, we see a cylindrical tank. This is a common site to store gas and oil. These two types of designs are used. So the question is, the question is, let's say there is a cylindrical pressure vessel that means like this, has an diameter 1.2 meters. That means if inner diameter is 1.2, we deal with radius, right? We deal with radius. So how much is radius? Radius is 0.6 meter and a thickness of 12 millimeter. So thickness is given as 12 millimeter. So is this thin wall? Because the theory we developed here can only be applied to thin wall pressure vessels. So if you divide radius 0.6 meter over, I'm taking my calculator, I'm taking 0.6 divided with 0.012, I got 50. Radius over thickness should be 10. So radius is 10 times thickness. So in the given situation, radius is 50 times thickness. So definitely it's a thin wall pressure vessel. Determine the maximum internal pressure it can sustain. What is the maximum pressure it can sustain so that neither it's circumferential nor it's longitudinal? So is circumferential is this. Hoop stress is basically circumferential stress. That means neither sigma 1 nor sigma 2 can exceed neither can exceed 140 megapascal. Neither of them can exceed 140 megapascal. For this to happen, what is P? That's the question. Which one is max? Sigma 1 or sigma 2? For given P, look at the formula. Sigma 1 is P times radius over thickness. Sigma 2 is P times radius over 2 times thickness. For a given pressure, given radius, and given thickness. Because in this case, radius, thickness are the same. And for given P, which one will be max? Sigma 1 or sigma 2? Sigma 1 will be max. Because sigma 1 is sigma 2 over 2, isn't it? So if you write PR over T to be sigma 1, because PR over T is sigma 1, so you can just say sigma 2 is sigma 1 over 2. That means sigma 2 is half of sigma 1. And given condition is neither sigma 1 nor sigma 2 can exceed 140 megapascal. If sigma 2 is 140 megapascal, how much is sigma 1? Is 2 times 140, which is 280 megapascal. So that means we have to say sigma 1 in this case cannot exceed. So sigma 1 is less than or equal to 140 megapascal. Only then the design will be safe. Otherwise, there's a possibility that this thing will blast or this thing will fail in circumferential direction. So sigma 1 should not exceed more than 140 megapascal. That means sigma 2 will be automatically be taken care of. So how much will sigma 2 be? If sigma 1 is 140, sigma 2 is going to be 70 megapascal. So sigma 2 is anyway safe. So the question is how much, so what is sigma 1 is nothing but P times R over T. Maximum is 140 megapascal. For this, what should P be? What is P? That's the question. So all you have to do is find P, assuming that the maximum stress is sigma 1 and that is 140 megapascal. So how much is P? P is nothing but 140 times 10 power 6 because this is mega. I'm writing mega to be 10 power 6 Pascal times the thickness over radius if you rearrange this equation. So Pu should be 140 times 10 power 6 Pascal. Pascal is Newton per meter square. Remember that? 1 Pascal is Newton per meter square. Thickness is 0.012. I'm converting millimeters to meters, and radius is 0.6 meters. This is meters, that is meters. So we get answer in Pascal. How much is this? Take your calculators. 140 times 10 to the power 6 times 0.012 divided with 0.6. I got 200. Let me 1, 2, 3, 4, 5, 6. I got 2.8. Pressure inside the tank cannot exceed 2.8 megapascals. If the pressure in the tank exceeds 2.8 megapascals, it will fail. And how did we calculate that? Based off the material we're using. Because according to the given condition, the so-called material, right, the so-called material or the material we used in this case has a property where it can't withstand more than 140 megapascals in circumferential direction. We have that information from whoever manufactured the tank. So based off this, we know that the pressure in the tank cannot exceed 2.8 megapascals. What about the spherical case? No, the spherical case, when it comes to spherical case, you only have one stress. You only have one stress, right? So that is sigma 2, which is PR over 2T. You only have one. So you don't need to remember 2 when it comes to spherical case. So that means if you take a spherical vessel, what is the maximum pressure that it can withstand? How do you do that problem? So when it comes to a spherical case, we have to use the formula, which is sigma 2 is P times R over 2T. Sigma 2 is P times R over 2T. You only have that. So this cannot withstand, so this cannot exceed 140 megapascals. That means we assume that the maximum pressure in the tank, spherical tank, is 140 megapascals. So the P pressure is 140 times 2T over R. So everything being the same, except you have this extra number 2. So basically P should get 5.6 megapascal. If you substitute T is equal to 0.012 meter and radius is 0.6 meter, you should get 5.6 megapascal. So if you take same material but make it spherical shape, you can withstand high pressure. You take same material but make it cylindrical, it can withstand only 2.8 megapascal. See, material is the same, thickness is the same, radius is the same, but the pressure that it can withstand is different. But the advantage of cylindrical is easier to transport, easier to maintain compared to spherical tank. Well, that is the case. So that is the answer. That's how we do a problem that involves thin-walled pressure vessels. Now, like I said in the introduction, let's go to a case where we have multiple stresses, multiple forces acting at the same time. Normal force is acting, shear force is acting, bending moment is acting, torsion is acting, all of them acting at the same time. Then what happens to that case? That's what we will see. Okay. So we have to do something called superposition. Superposition means, what is the concept of superposition? So what is the concept of superposition? That means you have a material, right? Take a point. On it, there is force P acting. Let me even more simplify. Let me say that there's some stress sigma 1 acting, and sigma 2 is acting like this. And there is a sigma 3 acting like that. So what is the net amount of stress acting on the point O? Let's call it O, on the point O. This is, so basically we take all the stresses in one direction. So if we take Y, we take net amount of stresses acting in that direction. That's basically superimposing. So sigma 1 going down, so let me write it negative. Sigma 3 going up, let me write it positive. So positive sigma 3, negative sigma 1, and I need to give you this angle, theta. If I give you angle theta, it's basically, because the area is the same, assuming the area is the same, sigma 2 cos theta is going down, so negative sigma 2 cos theta, right? So that is basically the net force acting in the y direction, net stress, I'm sorry, net stress acting in the y direction. And that's basically the concept of superimposing. So we calculate these stresses: stress due to normal force, stress due to bending moment, shear due to torsion, shear due to shear force, shear stress due to the shear force, shear stress due to torsion. We calculate each of them, and then we superimpose sigmas, we superimpose shear stress. So shear stress is different from sigma. So we superimpose sigma, we superimpose shear stress. So this one can be compression. So maybe this is negative, depending on the case. But due to bending, it's positive. So when we superimpose, we have to take positive for this, we have to take negative for that, depending on the case. And we will see different cases in the examples that I'm going to present now. Let's see that. So let's take a problem like that. I went over this problem in the introduction. Now, there is a 15 kilonewton force acting at an offset. So there is this, I'm just drawing this slightly bigger. Okay. So this is, let me give name for this axis. Let me say that this is X, this is Y. So this force is acting here. That's where it is acting. So it is on x-axis, but it is at an offset from y-axis by 50 millimeter, and that is 15 kilonewton force, and this is at an offset 50 millimeter. The other part is 50 millimeter as well. This one is 20 millimeter. This is 20 millimeter. Okay, this is the problem given. Now the question is, what happens to the point that is at C? That means that is here, basically here. I'm making a cut, BC. So whenever you make a cut, what should you draw? You have to draw three things. What is that? So whenever you make a cut in this B, C, you have to draw. So this is the axis. This is an axis that is parallel to Y. So I'm going to write Y dash, Y dash. And this is an axis parallel to X axis. So I'm going to draw this as X dash, X dash. Okay. Okay. Now, whenever you make a cut, you're supposed to draw three things. One is normal, the other one is shear, the third one is moment. And the reason for my assumption, why did I draw normal force into the section that I made a cut? Why did I not draw normal force like this going away from the cut? Because just by common sense, I know that 15 kilonewton on the top is compression. So to resist the 15 kilonewton going down, on the bottom, the normal force has to go up into the section to resist the 15 kilonewton. Just due to that reason, I just assumed it that way. So you can assume opposite as well, but you'll get a negative answer. What about moment? Why did I assume moment like this? With respect to y, assuming that this side is positive y. So with respect to positive y, assuming my I is the positive y, I assumed it's a counterclock moment. Why is it? Because 15 kilonewton is giving a clockwise moment with respect to positive y. To counter that, I have to assume something that is a counterclock moment. It just makes sense. That's why. What about the shear force? In this case, shear force would be zero because there is no force acting along XX direction. So we will just write sigma F, what should we do? The Z. So the rest direction that is left out is basically Z, right? Sigma of Z is equal to 0. Implies you have negative 15. Positive N is equal to 0. So we get N is equal to 15 kilonewton. Similarly, moments with respect to y-axis is equal to 0, assuming counterclock is positive, implies we have 15 kilonewton times 50 mm, so 0.05, right, 0.05 meter, and that is clock, so it's a negative, plus m is equal to 0. That's it, right? Because this n, the assumption is that this n is exactly acting at the centroid. So there is no offset for the n, assumed n. So there's no moment due to n, but there is an offset from yy. The 15 kilonewton is at an offset from yy. So we have this equation. So that implies what is M? Is 15 times 0.05 kilonewton times meter. How much is it? 15 times 0.05 is 0.75. So this is, till this part is basically statics problem. We haven't even entered mechanics part. Now the question starts for the mechanics part. What is the stress at points B and C? So at B and C, let's talk about C first. What is the stress at C? Can anybody tell me? By this time you have to assume, you have to guess. Due to this moment, due to the moment, and by the way, we got a positive answer. That means our assumption of this direction is correct. Due to this moment, what does it do to point C? Does it compress point C or does it expand point C? That means what is the stress due to moment? Isn't it my over I? If you remember, that is the normal stress due to moment. So my question is, does this moment here compress C or does this moment here elongate? Does this cause a compressive stress or tensile stress at C? This causes compressive stress. It clearly causes, so because you see, moment is going into C. Moment is going into C with respect to positive Y axis, or with respect to y axis, it is going into C. That means this is how things are getting compressed, direction into C, right? That means due to, so what is the stress at C? This is, first of all, number one, my over I, and this is compressive, isn't it? That is number one. Number two, what about N? What about N? Too many things here, let me, what about N? Oh, you may be thinking N is acting at this point. You may be thinking N is acting at that point. Is it? No, that is a normal force. Due to the normal force, what is the normal stress? Isn't the normal stress P over A, where P is the normal force, right? So in this case, it's going to be N over A. So what is the meaning of P over A? If you remember, if you understood the concept thoroughly, carefully, P over A or N over A is the stress acting on the entire cross section when there is a normal force acting at the centroid of that cross section. So due to this N, there is the stress acting on this entire cross section. There is the stress acting on the entire cross section, and that stress is N over A. Understand? So how much is N in this case? We got 15, right? We got 15 kilonewton. So what I'm going to do is I'm just going to write it as N over A. And even this is compression, isn't it? If you look at that, I assumed N was compression and I got a positive answer. I got a positive answer when I assumed N was in compression. When I assumed n is in compression, I got a positive answer. That means it is a compressive force. That means at point C, you have a compressive stress due to n, and you have a compressive stress due to m. M for mango and n for normal force. Right? M for moment. I don't need to say mango. M for moment and n for normal force. Okay? That means you have two compressive stresses acting at C. That means you have to add them both and write a negative in front of them because it's a compressive force. So what we'll do is the M is 0.75 times what is Y? Is Y 20 millimeter or 50 millimeter? Again, it is a test for your understanding of the concept. It is a test for your understanding of the concept, how much you understood. With respect to y axis, you have to remember one thing carefully, and that is this is the axis with respect to which the moment is acting. So with respect to that axis, you have to take everything. How much, where is point C with respect to that axis? How far is it? It is 50 millimeter away from Y axis, isn't it? But it is 20 millimeter away from X axis. So this is 20. Should you take that or should you take this? That is 50. You have to take 50 millimeter because we are considering the moment, and the moment is acting with respect to y dash or y dash axis. So we have to take the point C with respect to y dash axis, and it is 50 millimeter. That means y is 50 millimeter, by the way. That means I'm going to write it as 0.05. And by the way, this is kilonewton meter, and this is in meter over I. Again, it's a test of your understanding. BH cube over 12. What is B? Remember always B h cube over 12. B is always parallel to the axis of consideration. So for this area, this line is parallel to the axis, and that length is 20 plus 20, 40 millimeter. That means it is 0.04 millimeter. So this is going to be B h cube. H is perpendicular to the axis of consideration. So this is h. Then that is going to be 50 plus 50, it is going to be 100. So it is 0.1 cube over 12, BH cube over 12. BH cube over 12. So that is I. So my over I. Plus, so this is compression, right? Remember, this is compression. That means it is always better to write a negative, meaning it is in compression. Similarly, you have N is 15 kilonewton over area. What is area? It is nothing but 50 plus 50, 100. That means 0.1 times 0.4, 04, I'm sorry, 0.04 meter squared. So these both are negative. So add them both. Tell me how much you got. Don't be lazy. Take out your calculators. Do that with me as a practice. Divide with 0.04 divided with 0.1 cube 12. Times 12, and we have 15. Yeah, 15. The answer I got is 15,000 kilonewton per meter square. Let me check. Yes, that's right. 15 megapascals because it's a kilonewton. So what I'm going to write is 15 meganewton per meter square, which is going to be 15 megapascal because Newton per meter square is a Pascal. That is what is happening to the point C. What about point B? So here, what is happening to point B? Sigma B. Tell me how much is sigma B? Due to moment, what is the stress at B? It is tensile, right? It is trying to pull. This way, it is trying to pull. So B will be tensile due to moment, but due to normal, B will be in compression. That means the way we are supposed to write. So I think let me write for your sake. I have some gap here. So sigma B, if you take sigma B, my over I, this is going to be positive because it's tensile, but it's going to be negative for n over A because n is compression. But for C, I wrote both of them to be negative, right? I wrote both of them to be negative because C is in compression due to M. C is compression due to N. C is in compression due to both. But when it comes to B, it is tensile due to moment, but again compression due to normal. Okay. So that would be My over I, same drill, which is negative 15, no, positive 15, isn't it? How much did we get? Oh, no, we got 0.75, right? So we write 0.75. What is Y? 50 millimeter. So 0.05 over I. Same thing. Moment of inertia does not change. BH cube B is going to be 0.04. H cube is going to be 0.1 cube over 12 minus normal force is 15 over, and that is kilonewton, over 0.1, 0.04. So if we do this calculation, I just have to put a negative. I just have to put a negative in front of n. So I got 7500 kilonewton per meter square, which is basically 7.5 megapascal. So basically this concept is the superposition. That concept is superposition. Due to moment, it's positive, but due to normal, it's negative. But when it comes to C, due to moment, it's negative, and due to normal, it's negative. Both are negative. Okay. So that's how we do this problem. Again, if I ask you, okay, then where is the zero stress? So where is zero stress? So B is in, how much did we get for B? We got a positive answer for B, and we should get a negative for C, right? Negative for C, isn't it? So B is, let's say, positive, Let me write red color. B is positive and C is negative. So where is the 0 going to occur? Not exactly at X or Y axis, because this is only 7.5 megapascal, but this is 15, negative 15 megapascal. So where does it occur? You can apply similar triangles concept to find this length. And it seems we use similar triangle concept, we get 33.33 millimeter. So this is the location of zero stress. That is the location of zero stress. So any questions that you have in the video, always mail me for an appointment and I'll explain to you using MS Teams so that you understand the material wherever you don't understand. So using similar triangles, the height is 7.5. Let's take this as x. So basically we can write 7.5 over x is equal to, this height is 15 over, what is this? This is nothing but the total length is, how much is the total length? 50 plus 50, 100 millimeter, right? So we say this length will be 100 minus x, right? If you assume that this is x, how much will that be? The total is 100, so this will be 100 minus x. So that is how we can set up from similar triangles. And then when you solve for x, you should get 33.33 millimeter. So that's the whole concept of this chapter. When you have multiple or different loadings, you have to identify. That's all the problem. So all the problems that I present in slides and in the video lectures, please make sure you're able to follow each and every problem, understand each and every problem. So there is this tank in this example problem where due to what, so what is happening to A? That's pretty much the question. What is happening to A? So you have a tank. And what is happening to this point A, which is somewhere here? The radius is given as 600 millimeter. Thickness is 12. Isn't it thin wall? Radius is 600, thickness is 12. So radius over T should be greater than 10 to use our theory. So 600 divided to 12, I got 50. So we are okay there. So we can apply the concept of thin wall pressure vessel. And this is, what is this? Due to pressure. So the tank is not only till here, the tank is all the way till some place here. It is just that I only took that part. So whenever we make a cut, that means whenever we take only the part till A, because we have to make a cut to see what is happening at A. So when we make a cut, we have to write normal, we have to write shear, we have to write moment, right? Always you have to do three things, isn't it? Normal, shear, moment. Again, in this case, we'll have no shear. So at A, you have at A, you have the weight of the tank. There is this is 1 meter, right? And the thickness is given. That means this thickness. So there is some material on top of it. There is some thickness. So the thickness is given as 12 millimeter. And 12 millimeter thickness and 1 meter height, that means we can calculate the weight because we know the volume. There is this typo in the slide. There is this typo in the slide. This is, you see what is given here? Kilonewton, it is not times meter cube. What it should have been given is, this is the specific weight Y due to water and the specific weight of the steel. Specific weight, the units of specific weight is kilonewton per meter cube. So what it should have been given is 10 kilonewton per meter cube. It's a typo. It has been written as times meter cube. Just correct it. 78 kilonewton per meter cube. That is for steel. So what is the meaning of the specific weight? When we multiply this with volume that it is occupying, we can get the weight. It is in kilonewton. So we have to multiply with the volume V. Then if you multiply with the volume V, what we can get is the weight is nothing but, so weight of steel or weight of the material above point A is specific weight times volume of steel. Then we can get kilonewton. That is the force. Similarly, this is the weight of the tank, right? Above weight of tank above A. Similarly, what is weight of water above A? Specific weight of water times volume occupied by water. So let's do that. What is the volume occupied by steel? It is, isn't it pi times R2 square minus R1 square times the height, which is 1 meter? Isn't that the volume? Where R2 is the outer radius. How much is the outer radius? 600 plus 12, 612. Inner radius is 600 millimeter. Then we get the volume of the tank. Sorry, volume of the aircraft. It's the volume of the material of the tank. So what we get is we get this whole material. Then what is the volume of water? Volume of water is simple because you have, so this is water, this is what how much water is occupying. So volume of water, we can get that with nothing but pi r square times h, where height is going to be 1 meter, r is going to be 600 millimeter. And that's it. So when we plug in the numbers, we get what is weight of the tank above A. So the point A is here. The point A, so I'm going to remove the shear. There's no shear. The point A is there. So you have two things there. Number one, you have, due to the water above A, right? Due to the water above A, you get weight, but we need pressure, right? To apply the formula, to apply the formula, thin wall pressure vessels, we just need how much is the pressure at A from fluid mechanics. What is the pressure at A? Pressure at A is nothing but weight divided with area. So basically, you would be ending up getting just Y of waters. That means the specific weight of water times height. That is the pressure at A. That's how we calculate the pressure at A. So specific weight of water is already given. How much is it? 10 kilonewton, like I said, corrected per meter cube times H is 1 meter at 1 meter depth. So meter and it gets meter square. So we get 10 kilonewton per meter square is the pressure at A. So due to this pressure at A, we can calculate circumferential stress and we can calculate longitudinal stress, right? But in this case, we have no longitudinal because it is not closed. We just have the circumferential. We have the circumferential stress. How much is the circumferential stress? That means the circumferential stress would want to increase the radius. That means the stress would be like that. It's taking time to sync. Give me a sec. I drew arrows away from A along the radius. I think it's going to sync in a minute. So we can apply the formula sigma 1. Yeah, it got synced now. So it is trying to expand A. Oops. Yeah, it is trying to expand A like that. So we have circumferential stress, which is P times R over T. And we have normal, and normal is equal to, how much is normal equal to? Weight of the tank. So the normal is equal to weight of the tank, which is, this is going to be 78 kilonewton per meter cube times the volume. We get, so we get weight of steel. So pretty much 78 kilonewton per meter cube times the volume, we get the weight. Similarly, pressure is basically specific weight times the height. That's how we get the pressure. So sigma 1, which is the circumferential, is PR over T. Sigma 2 is weight. So let's plug in some numbers and let's calculate how much is weight of the tank above A, which is, let me plug in those numbers, 78 times pi times r square, 612, so 0.612 meter square minus 0.6 square. So I got 3.56. I got 3.5639. I'm going to write it as 3.56, and this is going to be kilo Newton, right? That's 3.56 kilonewton. That's what I got. Then that is the weight above tank A. Sorry, weight of the tank above A. So if you take the point, if you take this point A, due to this weight of the tank, right? it is undergoing a compressive stress. So if you take this block at A, from top and bottom, because bottom you have material, you have the weight of the tank, and the weight of the tank is being distributed over some area. And how much area is it? The weight of the tank is being distributed over this much area, isn't it? And how much is that area? That area is nothing but pi r2 square minus r1 square. So if you kind of make, if you're smart here, we just have to divide with this number. We just have to divide with that number. So which we will be left with 78 times 1, right? We are left with 78 times 1. So we should end up getting 78 pretty much. So this one should be 78 kilo Pascal. And that is due to weight of the tank. And due to the water, there is the circumferential, and that is sigma 2, or we should write this is sigma 1, and this is sigma 2. So sigma 1 is P times R over T. So P we just calculated to be 10 kilonewton per meter square. So we have 10 kilonewton per meter square. Radius is 600. So I'm going to write zero point 0.6 meter over thickness is 12. Am I right? 12 millimeters. So I'm going to write 0.012 meter. So let's do that. 10 times 0.6 divided with 0.012, we should get 500 kPa. So I got 500, because I have a kilo there, I'm going to write kilo Newton per meter square. So it is nothing but 500 kilopascal. Newton per meter square is a pascal. So sigma 1 is 500 kPa. And that is exactly how we get this picture. Similarly, this problem. So even if you look at this problem, if I ask you what is happening to the point C, right? If I ask you what is happening to point C, if you look at C from A to C, okay, let me redraw this figure. What is happening to point C means or determine the state of stress at point C. What is the meaning of state of stress? Give all the stresses at C. So basically here you have sigma and shear. Give me sigma and give me shear stress at C. That's pretty much the question. That means you have to first of all make a cut, and either you have to take a right part, that means starting from C all the way down, or starting from C to this point A. For me, the left part seems to be more simpler. So let me draw the left part. So the left part looks like this. So it is, so this is where C is. But because we're making a cut, let me give a 3D perspective. So okay, that is how it is. At A, you have AX and AY, right? What happens at C? At the centroid of the cross section, we have normal, we have shear force, and we have moment. And this is the point C. And how much is this according to the given picture? You have to understand the given picture. That is given as 50 millimeter. and this is given as 250 millimeter. Okay, because the cross section is given there. By looking at the picture, you need to imagine how the orientation of C is. So left top corner point is C. That is what is shown in the cross section figure given here. So how will you do the problem? To do this problem, that means to find N, to find M, to find V, three unknowns, you have to find what is AX and AY first. That means before you make a cut for this system, you have to find what is AX and what is AY. And because that is a statics problem, I'm not going to do it. You are supposed to do that. So this distributed load, which is 50 kilonewton per meter, it is acting on 2.5 meter length. So 50 times 2.5, what is 50 times 2.5? That is 125. So 125 kilonewton is acting exactly at the center. And that is what is shown. 125 is acting exactly at the center. And how did you get the slope? Because y is 1.5 and x is 2, and for something that is normal, that gets flipped. Y will be 2, x will be 1.5. Because I don't like decimals, I multiply that with 2 and I make y to be 4, and the 1.5 will become 3. And this is a common slope formula, 3, 4, 5. So this is how I have simplified the distributed load. And here, this is a roller support. That means you draw a normal reaction that is perpendicular to the roller support, and that's how we got. That's how we have to represent a normal reaction here and AX and AY there. Once you write this, you take a free body diagram and you write sigma fx equal to 0, sigma fy equal to 0, moment with respect to this point equal to 0, and then by solving you will find these reactions. And our goal is to find this AX and to find AY. And I'm not showing you how to do this because, like I said, it's a statics problem. Now we got AX. AX is 16.45 kilonewton. AY is 21.93 kilonewton. So pretty much we plugged in those both, and then now we can find what is V, right? What is N, what is M. By common sense, what I'm going to do is I'll change the direction of V, change the direction of N. The only reason because AY is going up, it makes sense shear should go down to balance. AX is going to the right, so N should go to the left to balance. This is by applying common sense. You can make any assumption. Moment, at this point, I just don't know. I'll just leave it as is. And then let's solve for N. What is N? Sigma Fx equal to 0, assuming this is our x-axis, that is our y-axis, and this is the z. So sigma fx equal to 0 implies ax minus n is equal to 0. So n will be equal to 16.45 because ax is 16.45 kilonewton. Sigma fy equal to 0 implies ay minus v equal to 0. That implies v is 21.93 kilonewton. Then sigma moment with respect to A, or with respect to, what point do I have? Exactly, A. with respect to A equal to 0. That implies V times C is at 1.5 away from A, right? So C, the point C, this one, is at 1.5 meters, right? That is 1.5 meters away from A. So that is at 1.5 meters away from A. So we get V times 1.5, and that is clock, so it's a negative, and positive M, because I assumed it's a counterclock, is equal to 0, implies M is equal to V times 1.5. That implies M is equal to, what is V? 21.93 times 1.5. Let's do that. Which should be 32.895 kilonewton meter. Now we got moment, we got normal, we got shear. Now tell me, what is state of stress? What is the meaning of state of stress? Like I said, state of stress is the representation of all stresses acting at C. That means shear and normal. Just tell me, what is the shear? What is normal stress at C? What is normal stress at C? Due to the normal force N, will C be in compression or tension? Normal force N is trying to compress the entire cross section. So the point C will be in compression, and the value of compression will be due to N. So what I'm trying to write is, what is sigma C? That means, what is the stress at C? The way we can find it is due to normal force over area, right? Just a second, I'm waiting for this to sync. Yeah, normal force over area, and this is negative because normal force is a compressive force. Then what about moment? Will moment, the shown moment, the moment is coming out at the bottom edge and going into the C. That means C is in compression due to M. That means even for M, you'll write negative M times Y over I. And moment is with respect to which axis? Is the moment with respect to Y axis, X axis, or Z axis? And at this point, that is something you should be able to tell me. Is moment, so here, this is X, right? This is Y, and that is going to be Z. So if you observe closely, it is not X, not with Y, but it is with respect to Z axis. So moment is with respect to Z axis here. So what is Y? Y is the distance of the point C from Z axis, which is 125. So Y is going to be 125 mm. What about I? BH cube over 12. How much is B? B is always parallel to the axis, parallel to Z axis. Z axis is 50 mm. That is B. What is height? 250 cube over 12. Negative. What is N? 16.45 kilonewton. What is A? What is the area? 50, 0.05 times height 250, 0.25 meter square, minus what is M, moment. Moment is 32.895 kilonewton meter times 250 times y is 0.125 in meters over 0.05 times 0.25 cube over 12. Do this and tell me how much you got. I'm going to use my calculator to do this problem. So supposedly we should get this answer. Let's see if we got that answer. So there's a typo here. This is 1 over 12. It is 1 over 12 there, not 1 over 2. I'm just verifying. Yeah, let's do that. So I got 16.45 kilonewton per meter divided with 0.05, 0.25, 32.895, 0.05 divided 0.25 cube times 12. 16.45 divided 0.05, 0.25, and 32.89. I got 64 for I got 64.46 megapascal. That's what I got. How much did they get? 63.16. We're close, but I got a different answer from what we got in the textbook. Maybe I did something wrong. Maybe I'm not sure. 16.4, 0.05, 0.25, that is meter square. And this is a negative, that means it's a compression. Okay. Then this is a 32.89, yes, times 0. Anyways, the concept is right, but I got slightly off. I'm not sure if that's a problem in the textbook or my calculation. I did it twice. I still get the same number. 16.44 divided 0.025 and divided 0.25. 32.89, 0.125, 0.5, 0.25 cube or 12. Yep, I still got the same answer. Anyways, the process, but the way we have to do the problem is like what I showed you here. This is how we calculate how much is sigma c. Similarly, what is tau c? VQ over IT. We know shear force is V, and V is 21.93. But what is Q? Q is Y times the area above the point C. What is the area above point C? There's no area above point C. So Q is 0. That means just you get 0 megapascal. So there's no shear. So this is how we have to do this problem, right? So the last problem is something similar to what we have done initially. So I'll allow you to do the last problem, but make sure you understand how to do this example 5, this problem. So when I say make sure you understand, you know what I mean. The final exam, you can expect a question of this nature, but I've given the solution here. So about what is the stress at C. Similarly, what is the stress at D? What is the stress at A? What is the stress at B? Try to do this problem. The solution is also available in the textbook. Do this problem. For any other questions, feel free to email me, reach out to me, and I'll explain in detail those concepts which you may have missed in the video presentation. Okay, stay safe, and that's it for this chapter.